In the second part to section 6.1, we're going to continue talking about discrete random variables and also introduce continuous random variables. Yesterday we talked about how to find the mean of a discrete random variable. And remember, we multiply each value times each probability and then add up all of those values to get our mean. Standard deviation, remember, standard deviation is how far a number is typically from the mean. So since we use mean as a measure of center for a discrete random variable, we use standard deviation as our measure of spread. The definition of the variance of a random variable is similar to the definition of the variance for a set of quantitative data that we saw in the past. So suppose that x is a discrete random variable whose probability distribution is as shown below. We know that the mean, mu sub x, is the mean of x, and we multiply each of our probabilities together times the value of x and add them together to get the mean. The variance is, as you would suspect, the difference in x from the mean squared times the probability. So it's the x minus the mean, the quantity squared, times the probability. And you add all of those up. So to get the standard deviation, we just take the square root of the variance. Looking at the baby's APGAR score example, we found the mean to be 8.128 back in the last video. To find the standard deviation, first we find the variance, where we take each x value. Right here, we took this x value, 0, subtracted the mean, squared it, and times by the probability. And we do that for every value. That gave us a variance of 2.066. When we square root that, we get a standard deviation of 1.437. So, a randomly selected baby's APGAR score will typically differ from the mean, 8.128, by about 1.4 units. If you take the problem that we did yesterday, when we made our histogram, it says, we define the random variable x to be the number of languages spoken by a randomly selected U.S. high school student. The table below gives the probability distribution of x. There's 5 languages, and then they gave us the probability. We're going to do 2 things. We're going to find the mean of the random variable x and interpret this value in context, and we're going to compute and interpret the standard deviation of the random variable x. So first we're going to find the mean, or the expected value. Okay, so taking our table, taking our table, if we want to find the mean sub x, or the expected value of x, we take each value, each language for x, and multiply by the probability. So 1 times 0.630 plus 2 times 0.295 plus 3 times 0.065 plus, and so on. I'm going to put dot, dot, dot. They don't like to show up. Plus 5 times 0.002. So the only one I didn't list was the 4. If you take your calculator out and add that all together to find the sum, we get a mean of 1.457. So this means if we selected many U.S. high school students at random, the average or typical number of language spoken would be about 1.457 languages. Now, we want to take that information and we also want to use that to interpret the standard deviation, to find the standard deviation and interpret it. I think it's easier if we do that by making a table. If we make a table, you can do it that way or you can do it all out. So notice our mean here is 1.457. I'm going to get rid of all of this writing so that we can, so I have more room to write. Okay, so now I'm going to take, to find the variance, remember our mean or our expected value was 1.457. So to find the variance, we take each language, so each value, 1 minus the mean squared times the probability. And we do the same thing for the second one. So this time we would take 2 minus the mean squared times the probability, plus dot, 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 and so on. 5 minus the mean, the quantity squared, times 0.002. So that gives me a variance of 0.0450. Oops, I'm sorry. 0.450. So to find the standard deviation, we'll take the square root of 0.450. So the standard deviation comes out to be 0.617. So if we talk about this in context, this 0.617, this 0.671, sorry, tells us the number of languages spoken by U.S. high school students typically varies by about 0.671 languages from the mean. Which is 1.457 languages. Okay, so hopefully this makes sense and you can see how we use the mean values, or how we find the mean values and the variance and the standard deviation and how to interpret in context. Okay, so now we've been talking about discrete random variables. Now we're going to talk about continuous random variables. So discrete random variables, if you think about it, they involve counting something, 1, 2, 3, 4. Situations that involve measuring something often result in continuous random variables. So a continuous random variable takes on all the values in an interval of numbers. The probability distribution of x is described by a density curve. Does that make any sense? Do you recall any density curves? The probability of any event is the area under the density curve and above the values of x that make up that event. Are you thinking back to when we made a bell-shaped curve, a density curve? The probability model of a discrete random variable x assigns a probability between 0 and 1 to each possible value of x. A continuous random variable y has infinitely many possible values. All continuous probability models assign probability 0 to every individual outcome. Only intervals of value have positive probability. So what does that mean? Think of our normal curve. The heights of young women closely follow the normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. Now, choose one young woman at random. Call her height y. If we repeat this random choice very many times, the distribution of values of y is the same normal distribution that describes the heights of all young women. So, what's the probability that the chosen woman is between 68 and 70 inches tall? So if we have a normal curve, you agree that the height